Hello, welcome to another video by Ozan Engineering. As you know, we're experts in all things Ansys, simulation with fluids, mechanical, electronics, and and others. Today, what I would like to talk about is electronics thermal simulation. We're going to be using classic Icepak, and the topic I want to talk about is how to model PCBs, how to import traces and vias, or ECAD models into Icepak. Then how to set up and execute the different types of operating conditions like forced convection or natural convection, etc. So as an introduction, what I'd like to talk about is PCBs and how to handle the thermals, because PCBs have a lot of layers, and it is fairly complex geometry when you want to resolve all those. So PCBs often have a large copper spread in the power and ground planes, and we do also have some vias, thermal vias, which can be effectively used to spread heat from the package. So a detailed conductivity map of the PCB is required to simulate heat transfer accurately. And this is essentially possible in Ansys Icepak using the trace import feature. In Icepak, it is possible to import trace layout of the board and compute the locally varying orthotropic conductivity on the board using a profile mesh size. And a lot of different import formats are available, such as ODB++, EDF, ANF, Gerber, Bol plus Info, and ICP 2581. So in this particular tutorial, we're going to import a typical PCB and solve two sample cases based on the trace layout information. And we're also going to see how to model layers separately for better accuracy. For this purpose, I've imported a model into classic Icepak. As you can see here, we have our heatsink, we have our board, we have our different components, and some connectors. We're now gonna go ahead start setting up the model. So the first thing we want to do is double click on our PCB board, and then what we want to do is, under the geometry tab, we want to import an ECAD file or an electronics CAD file. We can choose the type here. We're going to use Ansys neutral ANF. So I'm going to click that, and under the folder, I have this ANF file. So I'm going to tag this. What I'd like to do is I want to reposition the traced object, just in case if they're not in the same exact coordinate system. And similarly, we're going to turn the resize object on. So next step is we just hit open, and this is going to take a little while, and then it's going to import our traces into the domain. So this process can take up to a minute or two. So once it's done, it's gonna come up with a new window where you can see the imported layers and vias. At this time, what we want to do is let's correct the thickness information on the layers. So I'm just gonna punch in a couple of numbers here. And what we see is essentially the 7 layers are listed from top to bottom, and the materials are correct. You know, we're going to use copper and FR4 as our materials. And we have our grid density, so this has to do with the accuracy, where, you know, we're gonna define our mesh, and typically, you know, the guideline is for coarse mesh accuracy, we can multiply the minimum trace width by 4. And, you know, so for this model, this comes to about 0.5 millimeters, and I'm going to put that number selecting the grid density by size option. So we're going to model the layers separately, and then we don't need to recompute metal fractions. So I'm going to hit update. Then we can also take a look at our vias that are imported. So these also do make sense. So we can hit done. And then once it's done, we're going to say done for our circuit board. So here now what we do see is our traces and vias. We also have the option, so for example, we can hide them, or, you know, we can do a single color trace. We can do color by trace, which is the default. We can do a color by layer and color by net. So we have all these different options available to, you know, confirm that we got the right trace for the user. Another option to display the traces and layers, you know, in the perspective from thickness is as follows. What we can do is we can go to Edit, Preferences, and then if we go under Display, we can hit Display Traces in 3D, and then select this project. Then, you know, if we were to turn the model sideways, you know, if we look at it in the Y, let's see, if we look at it in the Y direction, so now we can see, you know, each of our layers. So we have our top, our bottom, and int 1 and int 2 layers, which we can see this way. Another thing we may want to look at is if we go under the model menu, we can hit show metal fractions, and then, you know, let's pick our object. Let's say, you know, we want to look at the top layer, and then if we hit display, it's gonna take a little bit to display, and what we can see is the metal fraction in our board. Now that we're happy with our import and traces and vias, what we'd like to do is build a conduction only model. So we're just gonna deactivate or suppress all the components except our board, and then we're gonna do a conduction only simulation. So for this, let me go ahead and mark everything but our board, and I'm gonna tick this. So now everything is, they're not deleted, they're essentially suppressed or placed under the inactive folder. And right now, you know, under our model, all we have is our cabinet and our board. So what we want to do is just have the same size for the cabinet as the board. So do a right mouse click on cabinet, select auto scale. As you can see now, the cabinet has shrunk down to the board size. Not only that, on the cabinet, I'd like to define some boundary conditions on the 6 faces. So for that, what we do is we go to the properties. And what we see is in the X direction, there's already an opening or an inlet-outlet pair, and all the rest are set to adiabatic walls. So what we're going to do now is we're gonna select min Z, convert this to a wall, and likewise max Z, we're gonna convert this to a wall. And we want to edit the min Z wall, where we're gonna assign, we go under the properties tab, and we want to assign this to a uniform temperature, and let's just set it to 20 degrees C, hit update, and done. Likewise, we want to go to max Z, and we're gonna hit edit under properties. Let's put in a heat flux of 20,000 watts per meter square. And we're going to keep this the cooling here. So we're going to hit done now. So next step is to generate a mesh around for our solution. We're going to go hit this generate mesh button, and what we've done is we already calculated the maximum element size as these numbers, so I'm just gonna put those in. So these numbers are has a good balance of cost and accuracy, and we want to resolve it much finer in the Z direction, obviously, because it's the thickness across our PCB. And let's also define our minimum gaps as this. So now we're going to use the measure HD method, and we can use all the defaults, and just going to hit generate. So this is going to go ahead and generate. What you can see here on the top right corner is the progress bar, and it went ahead and very quickly generated the mesh. We now have a mesh of around 200,000 elements, and you can also check the console or the message box down here. If there are any problems with the mesh, it's going to come up here in this region, and if they're printed in red, typically there's serious issues. And typically, you want to check your quality, and looks like, we have very good quality for face alignment and skewness. So that is great. So I'm going to go ahead and close this window. So once the mesh is generated, we do want to set up our problem, define the physics of our problem. So we go under the problem setup, and then we're going to hit basic parameters, where we're defining the problem now. In this particular case, we don't have any flow, so it's just conduction. We're going to turn it off. We don't need to solve for radiation, and that's pretty much it for the setup. We can hit accept. And next step is defining some solution settings. Let's go to our basic settings, and here because we care about temperature, it's best to put a tighter energy convergence criteria, and then hit accept. Then let's go to some advanced settings and select some appropriate options for our problem. Since we're interested in the temperature, let's change the temperature type to F. Let's put tighter criterion for termination and residuals. We always want to solve in double precision. Let's hit accept. So now our model is ready to be solved. Next step is we want to solve it. So we're going to go select this calculator button which says run solution. Let's call this, rename this as conduction case, and let's, before starting solution, let's make sure our mesh is appropriate. Let's quickly just regenerate our mesh. All right, so we're back to our 200,000 mesh. So let's go back, convection, let's start the solution. And yes, let's overwrite this. So right now what it's doing is writing the mesh and the case file in Fluent format. So model's going to be taken into Fluent. Ansys Fluent is going to execute the model. Once the execution is complete, it's going to export it back to Icepak where we can post-process it. So as you can see, as the Fluent job runs, it's going to pop up this window where it's going to go through these iterations, and very quickly within 6 iterations what we see is that temperature criteria is reached. So the solution stopped and it actually exported the results back to Icepak. So we can say done, and we can start post-processing. We already have a post-processing plane called cut1. So let's click on it. Typically at first we want to look at a variable for temperature. So I'm going to go ahead, select temperature, hit apply. So this is going to show us the temperature field due to convection, the higher and the lower temperatures. The results are as expected, so that's good. Another key solution might be the conductivity distribution in the Z direction. So the way to see it is we can, instead of temperature, we can go ahead, pick KZ, hit apply, and we can see the contours of thermal conductivity where it's higher and lower based on our traces. So this essentially concludes the first part with the convection solution. Next up, we're going to make some modifications on this model and then run a full conduction type solution. Now, so what I would like to do is I'll just hit close with these, and then I'm going to hide this, and what I'd like to do is activate all the components that we have. So right click, make them active. So now we have not only the board but also the rest of our system, and as you can see them here. What I would also like to do is go to cabinet, make sure that we have our min X, the flow boundary conditions, the convective flow going in the X direction, right? So let's do this. So right now, let's cancel. The first thing we want to do is auto scale. So the cabinet is, the size is increased, so it uncovers all the objects, not just the board. Then double click on it. Let's make sure the openings are right. Okay, in the minimum X face, that is shown in here. On this side we have the x velocity as minus 1.5, which is correct. So we can hit done, and now we can say done. So we're going to have convection. What we'd like to do is, now that the geometry is changed, we have to remesh our model, and we want to use coarser mesh because we do not need to resolve all the details as before, so we can get away with the coarser mesh. And let's put these numbers here, make it 0.7. Okay, so this is now allowed to grow the mesh faster. So I'm going to hit generate. And as you can see on the top right, it's going through the meshing process. We now have a higher number of elements since we have all these additional geometry. And we can again check the quality. You can also do a mesh display. Let's, for example, click display mesh. Let's look at it on a cut plane. And as you can see, it's essentially refining the mesh near different objects. So that's good. The quality looks good. So we can close this window. And because now we're going to add convection, let's double click problem setup basic parameters. We want to solve for flow, and we can stay with the zero equations. Turbulence model, radiation is off. Let's hit accept. In the solution settings, let's go back to our basic settings, and let's see. Okay, let's number of iterations 300, energy, so that all looks good. Let's hit accept, and we don't need to change the advanced settings. So then the next step is to run the solution. So we want to run a conduction case. So let's rename it to that. Start solution. And then right now, as I've said before, it's going ahead setting up the fluent model. It's going to execute it. This time the run is going to take much longer because of the higher mesh count, and also we're solving for flow, which adds essentially more equations, conservation of mass, UV, W momentum equations, and turbulence. So it's going to take much longer than the first run we did with conduction only. As you can see, during the solution process, we have our residual tracking window, and we're not only solving energy, we're solving for continuity and momentum equations as well. So it is going to take a while, and then once the run is done, we're going to move on to the post-processing stage. Now, we've reached 300 iterations. The solution has stopped. It is very close to convergence. Possibly, maybe, running another 100 or 200 iterations may be beneficial, but because this is a demo, we're satisfied with the current results. Looks, curves have flattened out enough, so we can just say done. Now we have our solution, and we want to look at temperatures, right? That's the main goal of this simulation. So what I'd like to do is go to post, and we're going to select an object face, which is going to bring up this new window, and then we want to select the object board outline 1. We'd like to see contours, select parameters. Almost always temperature is the main interest. Let's select this object so that the minimum and maximum is bound by the values of the temperature on this particular surface, and let's hit apply. Now what we can see is the highest and lowest temperatures on our domain. And this actually concludes our presentation for today. Thank you so much.